Hello everyone. In this lecture, we are going to talk about graph searching algorithms. That means we are going to talk about the breadth first search, that is BFS algorithm, and the depth first search, that is DFS algorithm. So starting with the breadth first search, in BFS what we have to do, we are provided with a graph G and a source vertex S. Then, with the help of BFS algorithm, we are going to explore the graph systematically in order to identify all the vertices which are reachable from S. In addition to this, we are also computing the distance of all the reachable vertices from S with respect to source vertex S. The basic logic on which BFS works is we have to discover all the vertices which are present at distance k from a source vertex S before discovering any vertex which is present at a distance of k plus 1. That means we have to discover all the nearest vertices to the S first before exploring any vertex which is at greater distances. Then once we are done with the execution of BFS algorithm on the given graph, we can compute the predecessor subgraph which is known as breadth first tree. And since we have started with a vertex S as the source vertex, the root of this tree it should be S. And it will contain all those vertices which are reachable from S. And the BFS approach, it works for the directed as well as undirected graphs. Next, we are going to start with the example. So first we will see how we can compute a BFS for any graph using pen and paper, and then we will go to the implementation part. So let's say we are provided with this graph and the source vertex to be used is S. Then we are going to make use of Q data structure in order to compute a BFS for any graph. And since we have just seen that the predecessor subgraph which is obtained using BFS is known as breadth first tree, and the source vertex which we choose for the BFS is going to serve as the root of this tree. So this is all about the initialization. Next, we have to repeat a set of steps till the Q which we are maintaining becomes null. And those steps are: first, we have to deq the vertex from the Q and add it to the BFS sequence. Secondly, we have to enqueue all the vertices which are adjacent to the dequeued vertex provided they are not visited yet. So in the present scenario, we have only a single vertex S present in the queue, as this is the starting vertex. So we will dequeue it and add it to the BFS sequence. Then S, it is adjacent to two vertices R and W, and we have not visited any one of these yet. So we have to enqueue R as well as W into the queue. So we will have something like this. We have dequeued S and added it to BFS, and then we have enqueued R as well as W in the queue which we are maintaining, and we have also marked these vertices in order to identify that we have visited them. And since as far as the breadth first tree is concerned, we are reaching R as well as W directly from S. So they should be present at the same level. Next, again we will deq R. So R will be added to BFS, and R, this vertex, it is adjacent to two vertices S and V, but S, it is already explored, so it will not be enqueued again. But V, it is not explored yet, so we have to add V to the queue. And we all know that we are using a Q data structure, so V will be added after W, that is at the end. So we have dequeued R, we have added V, and we are reaching V via vertex R. So V should be added as a child of R in the breadth first tree. Next, W will be dequeued. W is adjacent to S, T and X. S already explored. We have to add T and X to the queue. So W is dequeued. T and X, we have enqueued them, and we are reaching T and X via W. So T and X, they should be present as child nodes for W. Then we have to deq V. V is not adjacent to any of the vertex except R, and we have already visited R. So V, it will simply be dequeued, added to BFS, and no other vertex will be added after the DQ of V. So we have DQ'd V, added it to BFS, and there is no other change either in the queue or in the breadth first tree. Next, T will be DQ'd, and adjacent to T we have two vertices X, U, and third one is W. Out of these three, W and X, they are already explored. So U, it will be NQ'd, and accordingly breadth first tree will also be updated. So next, T is DQ'd and we have NQ'd U, and we have reached U via T. So U will be added as child of T. Then X will be DQ'd. The only adjacent vertex of X which is unexplored is Y. Rest all the other vertices, they are explored. So Y will only be NQ'd and accordingly added to the breadth first tree. So we have DQ'd X and we have added Y as a child of X. Now we have explored all the vertices, so now no NQ operation will be executed. Next, U will be DQ'd. All the adjacent vertices, they are already explored, so no change will be there. Then Y, it will be DQ'd, and the two vertices adjacent to Y are X and U, and they are already explored. So after this, the Q becomes empty, and the BFS sequence we obtained, it is this for the given graph using S as the source vertex, and the corresponding predecessor subgraph, that is the breadth first tree, is something like this. As far as the BFS sequence is concerned, then you may have several BFS sequences corresponding to a given graph and a given source vertex. One possible combination is shown here, which is bit different from the one which we have just obtained. However, both the sequences, they are valid, and the reason that there may be several BFS sequences, it is just because we can consider the vertices in any order. We can either visit R first, then visit W, or visit W first or R. So whatever sequence you wish to use, you can use that. Accordingly, you may have several BFS sequences. However, when we follow different BFS sequence, we may have different predecessor subgraph, but the distance of the vertices, they will remain same. For example, if we talk about this subgraph, here R and W, they are appearing at the same level. In this subgraph also, R and W, they are appearing at the same level. Then at the next level, we have V, T and X. So here also we have V, X and T. Then lastly, we have U and Y. Here also at the last level, U and Y are present. So the distance with respect to S, it will remain same in any of the sequence. As far as the breadth first tree is concerned, then you have to draw it only when it is asked. Otherwise, if you are asked to compute the BFS sequence only, then you have to simply give us this sequence, nothing else. But if we ask you to draw the predecessor subgraph corresponding to BFS, then only this tree is needed, else it is not needed. Secondly, when we talk about the distance of any of the reachable vertex from the source S, then we are actually talking about the number of edges we are visiting. So distance of U from S, it comes out to be 1, 2 and 3. We have to simply count the number of edges. So this is all about the undirected graph. Next we are going to look at the another example, and now we are going to start with the directed graph this time. So this is the given graph, and the starting vertex, it is given as R. So we will have a Q, and R, since it is the starting vertex, it has to be NQ'd, and accordingly the breadth first tree, it will have R as the root. Now we will DQ R and NQ the two unvisited adjacent vertices V and S. You can follow any order. You can either put V first followed by S, or put S first followed by V. Both are valid. So we have DQ'd R, NQ'd S and V, and since we are reaching S and V directly from R, so V and S, they will appear as child nodes of R. Then S will be DQ'd, and S, it is adjacent to only single vertex, that is W. So W will be added to Q and as a child of S. So we have updated all the things. Then V will be DQ'd. V is adjacent only to S and it is already visited. So we will only DQ V and no other change will be there. Then W will be DQ'd. W is adjacent to only T. So T will be NQ'd in Q. So we have NQ'd T and added it as a child of W. Lastly, when T is DQ'd, X will be NQ'd and it will be added as child of T. So after this, lastly, X will be DQ'd and then Q becomes empty. So this is the required BFS sequence for the given graph and R as the starting vertex, and this is the required breadth first tree. Again, this is not the only possible sequence for the given graph and starting vertex R. You may have different sequence also as it is shown in this table. However, in both the cases, the predecessor subgraph which you obtain, it will remain the same. So this is the process which we have to follow in order to compute the BFS of any graph using pen and paper. Now we have to look at the implementation of BFS. First thing, we have to represent the graph in the computer's memory, and we are assuming that the adjacency list representation is used in order to represent a graph. Then corresponding to each vertex, we are maintaining a few attributes. Basically 3 attributes we are maintaining, and these 3 attributes are, first one is the color. The color of a vertex can be white if it is not explored yet, that is undiscovered. It will become gray when we have discovered it for the first time, and it also signifies that the vertex may have some adjacent vertices which are still white in color, that is still they are to be explored. And lastly, color of a node can be black. That means we have explored all the adjacent vertices of that particular vertex. Then we are maintaining a pi parameter, which is nothing but the predecessor of a vertex. That means vertex via which we are reaching to this particular vertex. And then we are maintaining a distance parameter, that is d. It is just to compute the distance of a vertex with respect to the source vertex. And then the q which we are maintaining to execute BFS, it is identified with a variable q. So this is the procedure which we have to follow in order to implement BFS. So BFS, it will accept a graph G and a source vertex S. So G comma S. And then we have to set the attributes, that is the color, distance and predecessor to white, infinity and nil of all the vertices present in the graph except the source vertex. And then the initial values of source vertex will be, color should be gray, distance of a source node with itself, that is d, it should be equals to 0, and since it is going to be the root of the tree, the pi attribute, that is the predecessor of S, it should be equals to nil. Then we have created the Q, and then we will NQ the source vertex into it. After this, we have to repeat this set of steps till Q becomes null. So what we have to do, we have to DQ the vertex, and then we have to look at the adjacency list corresponding to the DQ'd vertex. So we are maintaining graph with the help of adjacency list, and this ADJU within the square brackets, it is used to represent the adjacency list corresponding to vertex U, and G is the graph. So V, it is representing any vertex which is present in the adjacency list of U. So for all the adjacent vertices, we have to check if their color is equals to white. That means they are still to be explored. So we are recoloring them to gray. Their distance, it will be updated to the distance of DQ'd vertex, that is U plus 1. And since we are reaching V via vertex U, so the predecessor vertex for V, it should be U, and after that we have to NQ that vertex, that is V into the Q. And after executing all these steps, that is the for loop from line number 12 to line number 17, we have to finally color the vertex U as black. And as far as the complexity of this algorithm is concerned, then all these things, that is line number 1 to line number 9, they are constant time operations, and we also know that how many times NQ will be done. It will be done for each and every vertex, and that too only once. So if we look at the complexity of this while loop, then it is executing the DQ operation. So how many times we can DQ? Definitely it will be equals to the number of times we are NQing. That means it is bounded by a factor of number of vertices in the graph. Then over all the executions of the for loop, we are only going to visit all the lists corresponding to all the vertices, that too only once, not more than that. That means we will visit each node present in the adjacency list of all the vertices only once. And we know that the total number of nodes present in the adjacency list representation, they are nothing but bounded by a factor of e. So overall complexity of this algorithm, it comes out to be order of v plus e. Now we are going to execute this algorithm on an example. So let's say this is the graph and the starting vertex, it is provided as S. So first step is we have to take the graph as an input in the form of an adjacency list representation. As we have already seen that we can take the vertices in any order, and here we are going to follow the chronological order. So we have arranged all the vertices in the alphabetical order, that are S, T, U, V, W, X, Y, and R, it is connected to S and V. So we have put the vertices in sequence in the adjacency list. Then S, it is connected to R and W. T, it is connected to W, X and U. So in alphabetical order we have U, W and X. Then U, it is connected to three vertices T, X and Y. Then V, it is connected to single vertex R. W, it is connected to three vertices S, T and X. Similarly, X, it is connected to four vertices and they are T, U, W and Y, and Y, it is connected to two vertices. So once we have created this adjacency list representation, then we don't need the graph anymore. That is the pictorial representation. So we are not going to make use of this graph now. We will work with the lists only. So first step is we have to initialize all the required parameters. So we will do the initialization part now. So all the vertices, they will have three attributes: color, distance from the source vertex S, and the predecessor. We have to initialize color to white, distance to infinity, predecessor to null. So we have done that for all the vertices except the source vertex, that is S. And for S, we have set the color as gray, distance as 0 and pi as null. Because we have just visited S, distance of the source node from itself, it should be 0 and it is going to be the root. So pi, it should be equals to null. Now we have to execute the set of steps till Q becomes empty. Since S is the starting vertex, so we have created Q also and initialized it with the starting vertex S. So next S will be DQ'd and we will work with the adjacency list corresponding to this S vertex. We can see that the first vertex which we have to consider is R. So first step is we have to check the color of the vertex. Via this, if it is equals to white, then only we have to recolor it to gray, update its distance and pi, and then NQ it into the Q. So since R, its color is white, so we have to recolor it to gray. Distance, it will be equal to the distance of predecessor node, that is S plus 1. So it will be updated to 1 and we are reaching R via S, so pi will have S. And then we have to NQ it into the Q, as well as we have to DQ S from the Q also, and we are assuming that while DQing, we are also giving the element as output in the form of an BFS sequence. These are the updates. We have updated all the required attributes of R. We have NQ'd R into Q as well as DQ'd S. Now we move further with the linked list of S. Now we have W. Again, color of W is white, so it will be gray. Distance will be distance of S plus 1 and pi corresponding to W, it will be S. And then we have to NQ W into the Q. So all the attributes, they are updated and W is NQ'd into the Q. And then we are done with the linked list corresponding to S. So what we have to do now, we have to recolor this U to black. So after the execution of steps for the two vertices, we have to color S to black. So we have to change color to black. That means we are done with the vertex S in the graph. Next, same process will be repeated for all the other vertices in the Q. So R, it will be DQ, and then we will visit the linked list corresponding to R. The first vertex which we obtain is S, but the color of S, it is not white, so we have to do nothing. Then we will visit V, its color is white, so we will recolor it to gray. The distance of V, it comes out to be distance of R plus 1, so we will have 2 over here, and we are reaching V via R, so pi will have R. These are the required updates. We have DQ'd R and NQ'd V. Next, we are done with the linked list of vertex R, so we have to recolor R to black. With this, we have completed with the vertex R. Now, W, it will be DQ'd. The linked list of W, it will have S, which we have already explored. Then it will have T and X. So, T, it is equals to white, as well as X, it is also equals to white. So, what we have to do, we have to color T and X to gray. Then infinity, that is distance, it will be updated to distance of W plus 1. So W, its distance is 1. So distance corresponding to T as well as distance corresponding to X, they will be updated to 2, and we are reaching T as well as X via vertex W. So pi will have W now. So we have first done the update corresponding to vertex T, and we have NQ'd T. Now we have to repeat the process for the vertex X also. So we have updated the attributes corresponding to X in the second iteration of the for loop, and we have NQ'd X also. So with this, we have completed the linked list of vertex W. So we have to recolor this W to black. Next, we will work with vertex V, and it has only single vertex R, which is already explored. So we have to do nothing. V will be DQ'd from Q and added to BFS, and for loop will not be executed for any of the vertex. So we have to simply recolor V to black. We have recolored V to black, and we have DQ'd V as well. Now comes the vertex T. It has first vertex, that is U, whose color is white. So it will be recolored to gray. Its distance will be distance of T plus 1, that is 3, and we are reaching here via T, so 5 have value T. So this is the update. We have DQ'd T and NQ'd U. Now further, so we will get vertex W, whose color is black. So we will move further. We will get X, whose color is gray. So we are done. Now we have to recolor T to black. So that's all for the vertex T. Now comes the vertex X. So vertex X, it will be DQ'd. The linked list corresponding to vertex X, it has T, which is already explored. Then U, which is also explored. W, it is also explored. And then we will have Y. So Y, its color is white. Recolor it to gray. Its distance will be distance of X plus 1, that is 3, and pi will have X. So we have updated all the attributes corresponding to vertex Y. We have NQ'd Y and DQ'd X. So now we are done with the linked list corresponding to vertex X. So we have to recolor X to black. With this, we have completed with the vertex X. Now U will be DQ'd, and U, it has 3 vertices T, X and Y. And since we have explored T as well as X as well as Y, so we have to simply DQ U and recolor U to black. With this, we have completed the vertex U. Similarly, if we talk about last vertex, that is Y, it is having 2 adjacent vertices U and X, and U as well as X, they are black in color. So we have to simply DQ Y and recolor Y to black. Now Q becomes empty, so we have to stop, and this is the required BFS sequence. Now if we have to create a breadth first tree corresponding to the BFS execution of the graph, then we can make use of this predecessor attribute of all the vertices in order to generate that graph. So definitely the root, it comes out to be S since its parent is nil. Then from S we can go to R, and from S we can go to W. So next level we will have R and W. From W we can go to T, as well as from W we can go to X. So W will have 2 children, T and X. So as it is shown here. Then From R, we can go to V. So V is present as a child of R. From T, we can go to U, and from X, we can go to Y. So T, it has its child node as U, and X, it has its child node of Y. So just by making use of this linked list and the algorithm which we have just discussed, one can compute the BFS sequence for the given graph as well as the breadth first tree. So again, it is just a simple implementation which we have considered. You can also implement the things on your own after understanding the BFS algorithm. Next, we have to start with the depth first search algorithm. So the depth first search, it says that we have to search as deeper as possible in our graph. Instead of exploring the graph breadth-wise, we are actually going to work with the depths now. So definitely when we have to work with depths, somewhere we are making use of stacked data structure instead of queue. And in DFS, we have to keep on continuing till we discover all the vertices which are present in the graphs. That means if in between we have reached a situation such that we cannot move ahead, but still there are some vertices which are still to be explored, then what we can do, we can pick a new source from the remaining undiscovered vertices and then repeat the process of DFS again. Since we may have multiple source nodes in case of DFS, so instead of getting a tree, we will get a forest. So the predecessor subgraph which is obtained using DFS is known as depth first forest, which actually comprises of several depth first trees. Again, DFS, it works with the directed as well as undirected graphs. So before starting with the examples, we will look at the assumptions on which DFS works. Again, we will assume that in order to represent a graph, we are going to make use of adjacency lists, and then corresponding to each vertex, we are going to maintain four attributes now. First one is the color, which can be white, gray or black again. White means yet to be explored, that is undiscovered. Gray means we have just discovered it, and black means we have completed the examination of that vertex. That means we have explored all the adjacent vertices of that particular vertex. Then pi, it is used to create the predecessor subgraph. So it will have the value of a vertex which is just visited before that vertex. And then we will make use of timestamp values. We have to maintain two timestamps corresponding to each vertex. First timestamp is D, which stands for the discovery time. That means we have to note down the time at which a particular vertex is discovered for the first time. Next timestamp, it is F, which is nothing but the finish time, which signifies that at this particular time we are done with the complete examination of that particular vertex. Okay, so we have to basically maintain this D and F. So let's say this is the graph for which we have to compute DFS, and as I said, we have to maintain two timestamps corresponding to each vertex, that is D discovery time and F finish time. So in order to maintain these timestamps corresponding to each vertex, pictorially we are going to make use of fraction where numerator will give us the discovery time, that is D, and denominator it will give us the finish time, that is F. So basically we will write D oblique F for each and every vertex. So this is the graph, and let's say we started with the timestamp value and we have chosen the vertex U as the starting vertex. So we will mark the discovery time of this U as 1. The moment we discover any vertex, we have to add that vertex to the DFS sequence also. So we have added the first vertex U to the DFS sequence. One can also visualize it as we have placed or pushed the first vertex into the stack. Next, from U, we can go to T, X or Y. We can work with any of the three vertices. So let's say we have chosen T. Okay, one more thing. Since we have started with U, so U should be the root. So we have added this U to the predecessor subgraph also. Okay, next we have chosen T. So that means we have discovered T now. So timestamp, we will increase its value by 1. So it becomes 2, and then At time 2, we have discovered this vertex T. So since we have discovered it, we have to add it to the DFS sequence. At the same time, what we are actually doing, we are putting this vertex into the stack, and we have reached T via vertex U. So we have added T as a child of U also. Again, from T, we can go either to W, X or U. Since U we have already explored, so we have to pick either W or X. So if you have observed, we are actually moving deeper with each iteration. Okay, so from W and X, let's say we have picked W. So again we have to increase the timestamp by 1, and discovery time of W, it comes out to be 3. Since we have just explored W, we have to add it to DFS sequence and push it onto the stack as well. As far as the depth first forest is concerned, we have to add W as a child of T. Again, from W, we can go to S, T and X. T already explored, so we have to pick either S or X. So let's say we have picked S. So increase the timestamp by 1. We will get 4. So we have discovered vertex S at timestamp 4. We have added it to the DFS sequence and pushed it onto the stack as well. And we have added S as a child of W. Then from S, we can go to R and W. W already explored, so we have only single option, that is R. So increase the timestamp by 1. We will get 5. So at 5, we have discovered R. Add it to DFS, push it onto the stack and update depth first forest by adding R as a child of S. From R, there is only single undiscovered vertex, that is V. So increase the timestamp to 6. Add V to DFS sequence and push it onto the stack. Now from V, we can only move to R, but R it is already explored. So basically we cannot move any deeper via vertex V. So we have to finish the examination of vertex V now. So in order to finish the examination, we have to update the finish time stamp of V, that is F, and we are using denominator to store the F parameter of the vertex. So we will increase the timestamp by 1 and store it as the finish time of V. So basically we have finished the examination of vertex V at timestamp 7. The moment we finish the examination of any vertex, at that time we have to pop that vertex from the stack. Initially V was here, but now since we have examined the V completely, we have to pop it out from the stack. Next, we have R at the top of our stack. So we will work with R now. Again from R, we cannot move at any other path because we have explored V completely. S, it is already explored. So now we have to finish with the examination of R. So again we will increase the timestamp value from 7 to 8 and store it as the finish time of R. At the same time, the moment we finish with the examination of vertex R, we have to pop R from the stack. So we have noted the finish time of R and popped it out from the stack. Next we have S. Again we have explored S vertex completely to mark its finish time by increasing 8 to 9 and popping it out from the stack. So we have finish time 9 and now S is not present in the stack. Next we reach W because W is at the top of our stack. So from W, we are done with S. We have discovered T also, but still we have one adjacent vertex which is still to be explored. So now we cannot finish the examination of W. We have to first discover X now. So this timestamp 9, it will be updated to 10 and then we will discover X at a timestamp of 10. We have discovered X. So X has to be added to the DFS sequence. X has to be pushed onto the stack and we have visited X via W. So X will be added as a child of W. Now again from X, we can go to 4 vertices. But out of these 4, there is only single vertex Y which is yet to be explored. So we will increase this 10 to 11 and discover Y at a timestamp of 11. Add the Y to DFS sequence and push it onto the stack. Plus, we have to add y as a child of x. Now from y we cannot move ahead. So we have to finish by increasing the timestamp to 12 and popping out y from the stack. Next, we have to work with vertex x. Again, we have to finish its examination because all its adjacent vertices, they are explored now. So finish time of x, it comes out to be 13 and we have popped it out from the stack. Next we have w. We are done with the examination of w now. So increase this 13 to 14 and finish w at timestamp of 14. Pop it out from the stack as well. Then t, we have to finish t at a timestamp of 15. Pop it out from the stack. And lastly, u is there. We have to finish the examination of u now by increasing the timestamp to 16 and popping it out from the stack. So the moment stack becomes empty and there is no unvisited vertex in the graph, we have to stop. Okay. So this is all about the DFS sequence. We have to arrange the vertices in the increasing order of their discovery time in order to get the DFS sequence actually. Okay, so this is the detailed process, but if you have to just compute the DFS sequence for the given graph, then we don't actually need this stack representation, because when we work with the implementation of DFS, then it is based on the recursion, and recursion, it implicitly makes use of the stack data structure. So the basic process is we have to simply note down the discovery time and finish time corresponding to each vertex present in the graph in order to get the DFS sequence. So now I'm going to discuss another example in which we are only going to make use of discovery time and finish time in order to get the DFS sequence. And the same process you also have to follow when you have to compute the DFS on pen and paper. And again, as far as the predecessor subgraph is concerned, you have to draw it only when we ask you. If we are not asking you for the predecessor subgraph in case of DFS or in case of BFS, then there is no need to draw these graphs. So let's say this is the graph we have to work with, and we have chosen any vertex as the starting vertex. What we are assuming in this example is we are going to follow the alphabetical order. So first vertex which we are going to start with is the A, and we have discovered A at a timestamp of 1. So we will put 1 at the numerator. Now from A, I can go to B, C and G. So alphabetically we have to work with B. So we will increase timestamp by 1 and mark discovery time of B as 2. So accordingly, B will be added as child of A. Now from B, we can only go to D. So increase the timestamp by 1 and mark discovery of D as 3 and also add D as a child of B. Now from D, we can go to C, E and F. So alphabetically, we have to work with C now. So we will discover C at a timestamp of 3 plus 1, that is 4. So we have marked 4 and add C as a child of D also. Now from C we can only go to B, but B it is already discovered, so we have to finish the examination of C now. So increase 4 to 5 and finish the examination of C. Now we are back to vertex D. So from D we can go to E and F. Alphabetically E will be chosen and it is discovered at a timestamp of 6, and also we have added E as a child of D. From E we cannot move anywhere, so we have to finish E now at a timestamp of 7. Now again we are back to D. From D we have to go to F now at a timestamp of 8. We have discovered F and we have added F as a child of D now. Again from F we can go to E, which is completely explored. From F we can go to A, which is in the process of examination. So we have to finish the examination of F now at a timestamp of 9. Now we are again back to D. We have discovered all the adjacent vertices corresponding to D. We have to finish the examination of D at a timestamp of 9 plus 1, that is 10. Now again we are back to B. We have explored the adjacent vertex D completely. So we have to finish the examination of B now at a timestamp of 11. Now again we are back to A. From A I can go to C, which is completely explored. From A we can go to G, which is yet to be explored. So we will explore G at a timestamp of 11 plus 1, that is 12. And then we have to as a child of A because we have reached G via A. Then from G we can go to E. It is completely explored. So finish the examination of G at a timestamp of 13 and then we are back to A again. We have discovered all the adjacent vertices to A. So we have to finish the examination of A now at a timestamp of 4. Once we are done with this process, we have the discovery as well as finish time of all the vertices. Now we have to arrange these vertices in increasing order of their discovery time. So let's start. So DFS, we should have A first. So A is there. We have 1. Then 2, B should be there. So after A we have B. Then we have 3, D. Then 4, C. And 5, it is a finish time of C. So we will search for 6. So 6, we have E. 7, it's the finish time. So we will search for 8. So at 8 we have discovered F. So after E, F should be there. Then 9, it is the finish time. We have to do nothing. 10 is also the finish time. 11 is also the finish time. Then we have 12. So at the last we are visiting G. And then 13 and 14, they are the finish time. So we have to do nothing. So you have to simply list out the vertices and their discovery time. That is the numerator values in this graph to get the DFS sequence. That means you have to simply arrange the vertices in the increasing order of their discovery time. So this is all about the computation of DFS for any graph using pen and paper. Now we are again moving to the procedure, or you can say the implementation of DFS. So DFS, it only accepts a graph G and no starting vertex is there. Then for each vertex we have to initialize color to white and pi to null. And we will make use of a timestamp value that will be increased each time in order to initialize either the discovery or the finish time of a vertex. And then for each vertex, what we have to do, we will check. If its color is equals to white, then we will call DFS visit procedure for the graph and the vertex U. And within this procedure, what we are doing, we are simply increasing the timestamp by 1. We are first initializing the discovery time of vertex to the updated time value. We are changing the color to gray and then we are checking the adjacency list corresponding to the vertex U. If the color of the vertex is white, we have to set the predecessor of the vertex to U and then we have to call DFS visit recursively for that vertex. Okay. So here recursion is there. So we are actually making use of stack which we have just discussed in one of the examples. So once we are done with the adjacent vertices of the vertex U, then we have to recolor U to black, increase the timestamp by 1 and then we have to use the updated time value to mark the finish time of the vertex. And we have to repeat this process for all the vertices. Again, as far as the complexity of this algorithm is concerned, then this for loop we are executing it for the order of V number of times. Similarly, this for loop, it will be bounded by a factor of mod of V. And similarly here, if we look, then all the statements, they are constant time operation, but we have a for loop at line number 4. And this for loop, what it is doing, it is visiting all the adjacency lists corresponding to all the vertices. Again, if we talk about the overall execution of this for loop, then we will visit each node of the adjacency list of all the vertices only once. So this for loop, it will never be executed for more than mod of E number of times. So here the complexity again comes out to be V plus E. Now again we are going to start with an example in order to execute the DFS procedure. So first step will be, we are provided with a graph. We have to represent it with the help of an adjacency list representation. So again we are going to make use of alphabetical order of vertices. So U, it is connected to V and X as it is a directed graph. Then V, it is connected to single vertex Y. W, it is connected to two vertices Y and Z. X, it is connected to single vertex V. Y, it is connected to single vertex X. And Z, it is only connected to itself. So once we have generated this adjacency lists, we don't need this graph. Next, what we have to do, we have to initialize. Initialize, that means we have to maintain 4 attributes corresponding to each vertex, and the color part of all the vertex, it should be equals to white, and pi predecessor, it should be equals to nil. Line number 1, 2 and 3. Plus we have taken a time parameter, initialize it to 0, and now we have to start. So let's say we are going to start with vertex U. So the color of this vertex, it is equals to white, so we will call the DFS visit procedure for the vertex U. So we have called the DFS visit procedure for the vertex u. So what it will do, it will increase the timestamp by 1, and the u parameter of this function, it is initialized to u, and after increasing the time value by 1, we have to set the discovery time of u to the updated time value. So we have initialized d corresponding to vertex u to 1, and then we have recolored u to gray. After that, we have to visit the adjacency list corresponding to vertex u. So u, first vertex which we get is v, and color of v, it is white. So what we will do, we will initialize pi corresponding to v to u, and here u is equals to u only. So we will update this u as a pi corresponding to vertex v, and after that we have to call DFS visit procedure for the graph and new vertex v. So accordingly, we will call the function again with the u equals to v. So what this function will do, it will increase the time stamp by 1. So initially we have time equals to 1. So we have increased time to 2, and we will use this time to initialize d parameter corresponding to the v vertex by line number 2. Then we have to update the color of v to gray, and now we have to work with the adjacency list corresponding to vertex v. So we are actually working with this linked list now. So we will get a node y. Since y, its color is white, so what we have to do, we have to update the pi attribute corresponding to y to u, and here u is nothing but vertex v. So pi corresponding to y, it will be updated to v, and then we will call DFS visit procedure again for this vertex. So now u, it will be called for a vertex y. So u equals to y now. The moment we call this function, what it will do, it will again increase the time by 1 and use this time as a d value, that is the discovery timestamp value for the vertex y. We will recolor y to gray, and then we have to look at the adjacency list corresponding to vertex y via the for loop. So again, we will get x, it is white in color, so we have to update the pi of x to y, and then we will call DFS procedure for this node x. So now u, it is updated to x, increase the timestamp to 4, and then 4 will be used to initialize discovery time of x, and then we have to work with the adjacency list of x now. So x, it has a single vertex v, but v, it is already explored. This for loop, it will not be executed for the vertex x. So now we have to recolor x to black, increase the timestamp by 1, and we have to mark the finish time of x to 5 now. We have recolored x to black and mark its finish time to 5. Now the control, it goes back to a point where we were executing for the vertex y. So after finishing the execution with vertex x, we are actually done with the function call, and we will return back to a point where u is equals to y. Okay, so we will again make use of a linked list corresponding to y. So y after x, it has nothing. So we are done with the execution of the linked list corresponding to vertex y. So that means we are actually done with this for loop. Now what we have to do, we have to recolor y to black, increase the timestamp, and use it as a finish time of y. So y, its finish time, it should be initialized to 6, and gray, it should be converted to black. So with this, we have finished with the execution of function call corresponding to vertex y. Now we have to return back to a point where u is equals to v. So we are at this point now, and again v, it has a single node y, which we have examined completely. So again we have to recolor v to black and increase the timestamp to 7 to initialize the finish time of v. These are the required updates. So again we are done with the function call with respect to vertex v. Now we are back to a point where u is equals to u. The linked list corresponding to u, it has two vertices v and x. We have just executed for the vertex v. So the next vertex in sequence, it comes out to be x, but color of x is not white. So we have to stop, and then we have to recolor u to black, increase the timestamp by 1, and finish the execution with respect to vertex u. So with this, we have completed the DFS visit procedure, which is called for the first vertex, that is U. So we are back to this point now. Since we are using an alphabetical order, after U we will check V. Color of V, no, it is not equals to white. So we will move ahead. Then we will reach W. Since color of W, yes, it is white. So we will call DFS visit procedure for graph G, W vertex. So we have U equals to W and timestamp, what it will do, initial timestamp value was 8. This function call, it will increase the timestamp value to 9. Use it as a discovery time of vertex W. We have recolored this W to gray and now we have to work with the linked list of W. It has first vertex as Y but its color is not white. So we will move ahead. We will reach Z. The color of Z, yes, it is white. So again we will set the parameter corresponding to Z to W. Okay. And then we have to call DFS visit procedure for this Z vertex. We will call the procedure for U equals to Z. Again it will increase the timestamp by 1 and use it as a discovery time for Z. Next we have to examine the adjacency list corresponding to Z. It has a single node Z. So it is already explored. We have to finish with the execution of Z now by marking the finish time to 11. We have marked the finish time to 11 and also recolored Z to black. So after this we have to return to a point at which we have called the function for vertex W. So U is equals to W now. Again W, we are done with the execution of all the vertices adjacent to W. So we have to finish the call for W now. So increase timestamp to 12 and mark the finish time of W as 12 and recolor it to black. So now we are done with the function call. We are again back to this point, but now all the vertices, they are black in color. There is no single vertex which is undiscovered. So we are done with the process. Now what we have to do, we have to just make use of this timestamp value corresponding to the discovery time of the vertices in order to arrange these vertices in the increasing order. So we will have U, V, then comes Y, X, W and Z. So we have U, V, Y, X, W, Z is the desired DFS sequence. Again, we can make use of this pi parameter to generate the depth first forest. Here, the first sequence which we have followed was, we started with U, then we went to V, from V we visited Y and from Y we visited X. So this is the first sequence and another sequence was, we started with W and from W we went to Z. So this is another tree. So since it is not a tree having single root, we have two depth first tree actually, and the complete diagram, it is known as the depth first forest. So these are the two algorithms which are used in order to search a graph. So again, for what you have to do, you have to first understand how to compute BFS, how to compute DFS using pen and paper, and then the implementation which we have discussed, you can use that implementation in order to write a program for both the graph search algorithms, though you are free to develop a logic of your own. But the core of the algorithm, it should remain the same. Thank you.